Okay, so we start just from here, electronic structure and bonding, the first chapter of the organic chemistry book by Pala Yukranis, 6th edition. This is so we will focus here electron structure and bonding acids and bases. Three structures you do see here. These are the showing electron density. Electron density they are showing, right? This one you do see is ethane, and what do you see in ethane here is you don't see like this red because ethane has just one single bond between carbon and carbon, so you have less electron density here. In ethene, what you will see is in ethene you have more electron density because you have double bond, and in ethane you have triple bond between carbon and carbon. So you do see here more light red color that's showing some more electron density. We now going to talk about what is organic chemistry and how the definition of the organic chemistry was changed. This is organic molecule, the urea. The first scientist who did prepare was Friedrich Wohler. This scientist prepared this molecules, Friedrich Wohler. And from where did he prepare? He prepared from an inorganic molecule which is ammonium cyanate. And what is the ammonium cyanate? This has one, ammonia positive ion, another is a cyanate, OCN negative ion. So the total, this is a neutral and plus and negative, ammonium cyanate. So what is actually going on? How did he prepare this urea from ammonium cyanate? What happened? Oxygen has here one friend which is a cyanide, and oxygen on other side oxygen has ammonium another friend. So what happened when it was heating? Heated. So there was a lot of energy going on, and then each of the these atoms start running, and they start separating, rearranging. What happened? Carbon oxygen was very close friends, right? The oxygen has quite good electronegativity. So oxygen said, I'm not going to leave you, carbon, I love you. So what happened here? You do see a carbon oxygen double bond. Now the other thing, one side was nitrogen, right? Another side was nitrogen. Nitrogen ran away and goes to the ammonia and say, ammonia, oh ammonia, you have four hydrogen, right? Can you give me two? We both share. I'm hungry. I need two hydrogen. And the carbon, I have to make a single bond with the carbon, and can you give me two hydrogen please? And what happened is this NH2 gives two hydrogen, and you do see here, no, they are quite friends. They both have shared their hydrogen, and now you see two hydrogen, right, with each. This is so you do have one NH2, another NH2, and carbon is in between, right? So carbon has now four bonds total. Two it is forming with an oxygen. Here carbon was, next to oxygen. That's fine. But only thing what happened was nitrogen took two hydrogen. So urea's bonds is a rearrangement, of the bonds by heating. And what is this? Urea is an organic molecule. But before, no one knows that you can form an organic molecule, from an inorganic. So, what was the chemist believing then? I'm going to show you what they believe. Chemists could not create a life in the laboratory. In laboratory, they could not form a molecule, with it does exist in living organisms, which living organism produce molecules. The chemists couldn't do that in the laboratory. Then what they thought? They thought, we can't do that. Then they said, why we can't do that? Because if you want to create a compound, natural one, you need a vital force, and that vital force just exists in nature. And we don't have that vital force in the laboratory. That's the reason, we do our best, but we can't make the organic molecules. But they were surprised with this mindset. They have a belief, right, that we can't make organic molecules. They were. You can imagine how surprised they will be when this scientist break the record of their belief. Frederick Wöhler in 1828, he was doing experiments, and he came across the ammonium cyanide, this little boy, and he heated this one, and he was make this, molecule urea. We discussed how it was. We can arrange this molecule ammonium cyanide to urea, and this Friedrich Wöhler was, very happy, excited. He was the first person to produce a urea, which is an organic molecule, And how did he produce? By heating. And this urea, is excreted by the mammals from urine and other, waste products. There is a urea, but this was before, so scientists considered no, you can't make a urea. Urea, animals make, right? It does exist in living organism, but when this scientist, Friedrich Wöhler, heated this um, ammonia, ammonium cyanide, and he gave us the urea, then our belief changed. We say that from even inorganic we can make organic. That's what happened. So first time, what we said, the first time the organic compound had been obtained from the something other than the living organisms. That was the amazing thing. You do have an organic compounds, and we don't need living organisms here. Certainly there is no any aid of any kind of vital force, which we were talking about. We were saying we do need a vital force, but what happened here? We make this molecule, did we? So we make a urea, and we didn't use a vital force. We are scientists, are we? So what happened then? Organic compound definition. Before we said, okay, vital force needed is very important, natural force. If you want to make an organic compound, but now we're going to say no, that's not important. So what are we going to say now then? We're going to define the compound, the organic compound that contain carbon. So we're going to change our definition, can we? So what are we going to say is organic compound are defined as a compound that contain carbon. You can add a carbon as an essential element. So they're going to have a carbon necessary element, essential element. So the definition changes when this scientist did this job. I hope you will do something new like that. Now we're going to focus and just about something else in this book. We're going to talk about what this little table is. This one, second row of periodic table. This is, you do see here, you know, all the atoms, carbon in the mid here, in the middle, and you three atoms on this side and another three on this side. This is lithium, beryllium, boron, carbon here, and then what else you do have is nitrogen. In the period you are moving, you're walking towards your right side, you do see oxygen. You at fluorine you stop, and if you wanna go back, oxygen, nitrogen, carbon, you stand a little bit, but you move towards boron, beryllium, and lithium. What are we going to talk about here? What's the point of drawing this period, the second row of the period? See, the thing we're going to talk about is carbon position in the periodic table. So where is the carbon? Carbon is here. So carbon position in the periodic table, and what does it do? Carbon is in the center of the second row of the elements. This is second row, and it is in the center, and the atoms on the left carbon and the to the left carbon. So you will see this is the left of the carbon. They have, what do they have? They can give up electron. So on the left they can give up electron, while atoms to the right have the tendency to accept electron. So this is the left, they can give electron. Why they can give electron? Well, they do love electron, but not that much as carbon. So they are less They love electron but less. So if electrons say I wanna go, they don't really care. They say okay, we'll let you go. And same does the beryllium is more electropositive. We say they have less electronegativity. Electronegativity is ability of the atom to attract the electron towards itself. But here lithium, okay, if you want to talk about lithium, they can give electrons. They are not very electronegative. They say, okay, we are on the left, extreme left of the carbon. We can give electron. We'll let you go. So what do? They have a tendency to give electron, right? By this one, if you're talking about this one, they attract the electron more. They love electron, and then they don't let them go, but they accept electron. So these atoms can accept electrons. That's what we're talking about. They have a tendency. They can do that, accept electrons. If you're talking about the atoms in the period on the right side, this is the right side of the carbon. What are they going to do? Fluorine is most electronegative, love more electron. They're lover. They're not haters. They're lover of electron. They love. They say, come on, electron, come on, we love you. Come on, sit here and stand, sit, love with us. So that's why these three atoms you do see, they will accept electron. Now, why the carbon is the middle and what's the benefit is that's what here is told. The carbon is in the middle, right? Neither readily give up electron nor readily accept electron. This is like in the middle. This neither give up electron like that and nor accept electron very quickly. This is in the middle. So what is the benefit? Then it shares the electron. It say, okay, we share. I'm not going to give electron like these guys. Neither I'm going to accept full electron, but I can share. If you want to eat with me, I'm not going to give the whole of my food to you guys, right? And neither I'm going to do like that. Like I'm not going to do like give my whole food or take whole food, but what here they we can say take whole food here, give more food. But what I'm going to do, we can sit together, right? You and we together eat. So what we're going to do is we're going to share electron. And that's what we're going to do with several different kind of atoms. Okay, I'm carbon, right? Nitrogen, come on, share to me, I can do that. Oxygen, come on, we eat together. Fluorine, come on, we share electron together. Boron, if you want, come on. So this is the carbon is like that. It's saying, okay, come on, we share the electron. And it can share electron with other carbon atom as well. So if other carbon comes here, okay, oh carbon, I wanna share this electron. Carbon will say, okay, carbon, I'm a carbon. You carbon too. Let's we sit, we eat together, like the way you eat in a restaurant, do you? So this carbon is quite friendly type guy. I say, no, I'm not going to give electron, right? Either now I'm going to accept electron like this, guys, but what I'm going to do is I'm going to share. I will hold my electron, and you hold your electron, and we sit together. We talk together. We eat together. That's what this carbon is going to go. It's a quite good guy, and that's why it is quite famous. You will see in many compounds. Carbon sharing electron, forming bond is a wonderful guy you will ever see. So it can share electron with other carbon atom. That's absolutely amazing. Then what's going to happen? Consequently, carbon is able to form million of stable compound. Like very friendly, person can make so many friends. So carbon share electrons, a million of compound. You will see the carbon stable compound. So carbon is a good guy with a wide range of chemical properties, a different property you will see, and by sharing electron, that is amazing. Now we're going to move further and we're going to talk about structure, little bit of an atom. What is the structure of an atom? An atom consists of a tiny dense nucleus. Nucleus is quite dense, it's a tiny one. That's what the atom is. So atom has a nucleus, but there's a tiny one. I'm going to show you somewhere. if nucleus comes. But now we're going to talk about just the nucleus. It's tiny, it's a little small, but it's dense, it's not much space there. So what is there in the nucleus then if no much space? Is the nucleus has a proton and neutron, and who surrounds the nucleus is electron guy. Electron guy, they keep circulating the nucleus. They say, okay, we run around you, we move around you, and the nucleus is quite tiny, and that are spread through the relatively large volume of space. Who are spread? The electron, a large volume of the space, electron enjoying their life. They know they are moving, they are wandering around the nucleus, and they are saying to nucleus bye bye. Sometimes they leave them, sometimes they come towards the nucleus. So electrons are moving. Nucleus uh, contains positively charged. Nucleus contains positively charged proton. Proton lie in the nucleus. They love nucleus. They are inside the nucleus. They have positive charge. And neutral neutrons. Neutrons are there as well, but they don't have any charge. So in nucleus you will see two things. One is a neutron which doesn't have any charge. Another thing you will see is a proton which has positive charge. So what the is the total charge and nucleus is going to be positive. Why it is a positive? Because nucleus has two things. One is a neutron, right? A neutron doesn't have any charge, and proton has positive charge. So total charge and nucleus is going to be positive. And you have electron which are enjoying their life around the nucleus. They are throughout a large volume, and they are moving there in a space around the nucleus. They have a negative charge, so total charge on atom is going to be neutral, because positive charge is on the nucleus and the negative charge on the electron which are surrounding the nucleus. The electrons are negatively charged because the amount of positive charge on a proton equals the amount of negative charge on electron. So each proton has a unit positive charge, each electron has a 1 unit of negative charge. So if electron and proton is equal in number, you're going to have total zero charge. A neutral atom has an equal number of atoms. We're going to talk about the neutral atom. If you do see a neutral atom, what are you going to have? A equal number of proton and electron. That's right, because then you will add the number of positive charge and number of negative charge. What will you see? It will be zero. So neutral. An atom can gain electron and thereby become negatively charged. If you give electron to the atom, then electron has a negative charge. What's going to happen? The negative charge is going to develop an atom, and we will say if an atom gain an electron, like it's the same way like if you have a bank account, right? If you give an electron, if you spend more money, your account goes negative, does it? But electrons are here negative things. So wherever they go, this is like a debt, I can say, if you compare with the bank account. So if you take more electron, it means you're taking more debt, right? So you're spending more money. So if atoms gain elected, mean they are getting something negative. They're spending more money. Although this is just an example, I can give you. But electron, wherever go, they give a negative charge, because electrons have a negative charge. That's why the charge you will see an atom, more electron will be negative. And if they are going to lose electron, if negative charge is away, the people who spend more money they are away, then what's going to happen to the atom? Atom will be happy. Would it be? Then what will be? Then if goes electron, the charge is going to be positive. So they are quite positive. So electron are the guys who give a negative charge, and if they come negative, if they go, is going to be positive charge, because they take the negative charge with them, and what is left is behind positive charge. However, the number of proton in an atom doesn't change. You won't change the number of protons. Only thing changes number of electron. Proton and neutron have approximately the same mass. So proton and neutron have approximately, if you weigh them, if they are the same heavy, same weight, approximately 800 times, quite heavy. Heavy guys, right? And they are heavy. This could be the reason they don't leave the nucleus. They are quite heavy. They can't walk. The like if someone is overweight, quite 800 times is difficult to walk to lift the weight. So here is the proton neutron, fatty guys, quite big guys. And what they do, they are lazy. They don't wanna walk. They can't walk. So what they do is 800 times more massive than electron stay in the nucleus. This means the most of the mass of an atom is in its nucleus. We said tiny nucleus, right? They are tiny one, but they have the same number like electrons, and they are heavy as well, 800 times heavy, right? And in a tiny space both are number of electron and proton and neutron, sorry. Electrons are away from this tiny space, this dense. That's why we said dense nucleus, right? So dense nucleus, you're going to talk about proton and neutron have approximately same number. They are lying in the nucleus, and they are massive, 800 times heavier guys. Electron quite smart. They are on a diet. They are very careful of the weight. They run all the time. They are running, so they are very health conscious. That's why you see them lighter, but they are too light, 800 times. So that's good for them. This means the most of the mass of an atom. Whose guy is going to contribute toward the most of the mass? Who is going to be contribute, if I ask you, is in the nucleus, and the guys who are responsible is the proton and neutron. They are heavy guys. They don't move much, right? They are heavy people, right? However, most of the volume of an atom is occupied. So if we talk about volume, space, who occupy the volume, who occupy the space of an atom? So is electron, because they are moving, they're going from one room to another, right? They are very active, athlete, guys, health conscious, not having more weight. 800 times less weight. How good are they? Well, they are moving, so more space is occupied by them. The volume of an atom is occupied by electron, and that is where our focus will be. So we're going to focus mostly on electrons, right? Because they are occupying more space, right? Volume of an atom. They are healthy guys. They are athletic. They are moving, right? We love moving things, do we? And they are going to form a chemical bonds. Electron going to form a chemical bond. So we are talking about structure of an atom. So we do know something right now, and we move forward. What is atomic number? A first question. Well, someone got a Nobel Prize for these things, but I hope you will get two for something you develop. We're just going to talk about atomic number right now. It's amazing. Can you guess what atomic number is? Well, if you I hope you will, but I'm going to tell you. There is an atom. We love atom, do we? An atom has equal number of proton. Atom has number of proton, and those protons are lying inside the nucleus. Number of protons. And in the nucleus, wow, they are in the nucleus, are they? So number of protons. Equal number. We're saying equal number of protons in the nucleus. To equal to what? Equal to atomic number, right? So if I say 6 atomic number, is means that atom has 6 protons. Like if we talk about carbon has 6 atomic numbers. So how many protons you will see? 6. Wow, good, well done. You did answer the question. Well done. Right, you're a good student, right? Atomic number is also the number of electron. So atomic number is also the number of electron. Do you think it's going to be always? Not. But it's the number of electrons when when it is a neutral. Uh, when atom is neutral. That's what we're going to tell. Right. So we are saying the atomic number is also number of electron that surround the nucleus. So if someone asks you, do you think atomic number is going to be number of electron? We can say that's around the nucleus, the neutral atom. If atom is neutral, of course, the number of proton and electron going to be the same. Then we can say, okay, if neutral atom and whatever electron you tell me, that is atomic number. I'm the winner. I'm the winner student, right? Because I tell you the atomic number. Did I tell you? Did I? Yes, you told me, right? So if you see the number of protons, This is the atomic number, but if you see a neutral atom and whatever number of electrons the neutral atom are, this is the atomic number as well. For example, if we talk about carbon, how many electron, proton it does have is 6. So this is the atomic number, which means that the neutral carbon atom has 6 proton. Is that right? So 6 half a dozen proton and 6 electron. That is a good, well done. Because the number of proton in an atom doesn't change number of proton. You won't see the change in the number of proton. They are quite heavy, guys. We did notice they're 800 times heavy than electron. They don't want to move. Why they should move? They love nucleus, a tiny place where they're living. So what happened? The number of proton don't change. They don't move. They don't leave the nucleus. They don't leave the atom. The atomic number of particle elements. So we're talking about atomic number of a particle element is always the same. Why? Because the number of proton doesn't move, so atomic number is going to be same. All the carbon atoms have the atomic number of 6. If we're going to talk about carbon atoms, all the atoms are going to have atomic number of 6. So we have covered the definition of what atomic number. What is atomic number? It's a number of proton. That's very simple number of proton in a nucleus. We can also say is also number of electron surrounding the nucleus, but only if the atom is neutral. That's it. And what is the atomic number? What do you think? Atomic number is the sum. We're going to add two things. One is a proton, another is a neutron. And if you add up, well done. You're a good student. You did add up two things. One, you added a heavy guy, which was a proton. Other, you added another heavy thing, a neutron. And whatever number is, that's your mass number. That's the mass number. So you are going to add two things. Number of proton in the nucleus, number of neutron in the nucleus. Suppose it is a 13 carbon, right? Mass number. So this means carbon has 6 proton, right? And 7 neutron, total 13. Not all the carbon atom have the same mass number. That's what you're going to find. Because number of proton and number of neutron is not going to be same for all the carbon atoms, then mass number is not going to be same. Atomic number will be the same. So here we are saying because and even though they all have the same number of protons, all the carbon atoms have the same number of protons, they do not have the same number of neutrons. That's why the atomic mass, if we talk about, that's not going to be same for all the carbon atoms. For all the carbon atoms, for example, 98.89, this is high percentage of naturally occurring carbon atom. If we check the carbon atom naturally occurring, majority of them 98.89, this is nearly 99%, right? Only 11 point 11% less. So what are they? They have a 6 neutron. Wow. So if you add 6 plus number of neutrons plus number of proton, how much is going to be? 12. So 12 atomic mass, you're going to have abundant, a mass number 12. We say 12, and 1.1% have this 7 neutron. So this one is the highest percentage, right? And this is a 12, where number of proton and neutron total is 12, but a less percentage. This is just 1.11, right? Very few percentage. What do are? They have 7 neutron. And what will the mass number if you have 7 neutrons? Good students. How much will be? What do you think? It's going to be, of course, 6 plus 7 is just mathematical. We're going to add two things. 7 plus 6 is going to be 13. Well done. So 13 is the atomic mass. But what percentage of the naturally occurring carbon atom? 1.1%. You won't see, in high percentages, it's quite less. But the most abundant you're going to see, the 12 atomic mass, 12. That's what you're going to see. So what we do say to these all the different carbon atoms, mass number of 13, and you did see the mass number of 12. Can you guess? Can you predict? Well, two different kind of carbon atom. We talk about 12, we talk about 13. What are they? They are isotopes. So now you can define what are isotopes because they have different mass number. But why? So we can say isotopes definition, right? Is the same atomic number. We do know atomic number is number of proton, right? They are the same, but there is something different. What is that? Different mass number. Why? Because they have different number of neutron. That's why. So mass number, when we add neutron and we add proton, the number change. Although number of neutron 7 is quite less, it's just 1.17, but these friendly guys, they are in less. This number 13, their percentage is quite less, but they do exist. So what are they? They are isotopes. What are the isotopes? They are atoms which have the same atomic number. Isotopes, what are they? They are the same atomic number, right? They have same atomic number, but number of protons, that's mean number of protons same, but different mass number, because they have different number of neutron. So they have different mass number. Why? Because they have different number of neutrons, right? So if someone asks you what are isotope, you're going to say they have the same number of proton, right? But they have different mass number. And why they have different mass number? Because they have different number of neutron. And we're going to talk about chemical properties of the isotope of a given element are nearly identical. So if you talk about chemical property, they are going to be the same. Neutron, they are neutral, they're not going to do much change. They're not going to bring much change in chemical properties. So what will you see in the chemical properties of isotopes? What will you see? You will see the same, nearly identical chemical properties. That's quite good, isn't it? So naturally occurring carbon atom also contain trace amount of 14. You will be surprised. So, and other isotopes we do have, this is just 14. Naturally occurring, so it has a little amount which has 6 proton. Of course, if you're going to give the 14 atomic mass, right? Not numbers. This is going to be atomic mass. Then how many neutron you're going to have? 8. Well done. So you're going to have 8 neutrons, right? This isotope of the carbon is radioactive. It emits radiations, right? Decaying with a half-life of so many years, 5,700 30 years. What is a half life? Half life is the time, half time, right? Half life is the time it takes for one half of the nuclei to decay. So if someone asks you what is the half life, well, common sense half life tells you the total life and half of that. But what is the total life when something exists? If we have a life, suppose we are going to live for 100 years, what is the half life? 50 years. So these are the radioactive isotope of carbon, right? They have different mass number, which is a 14, and they're going to decay, right? They're going to decay because they are radioactive. They emit radiations, right? And they're going to be converted to carbon normal 12. But when they are decaying, but they will 5,730 years. So this is 6,000 years but less. How much less is? 270 years less. So 730, right? 730. So it's 270 years less than 6,000. And this is their half life. Mean they're going to decay half. And so half number you will see. You will find the half number of these isotopes left after so many years. So half-life is the time it takes for one half of the nuclei to decay. So total nuclei, but one half will decay, right? During this so many years. So they decay not very fast. So many years, you can't imagine. So many years, 5,730 years, they're going to decay, but how much? Just a half, right? As long as planet of animal is alive, as a planet or animal is alive. So if we talk plant or animal is alive, right? They are still there, and they are going to decay. But this means, wow, what do you think then? From half life, then you can find the age, and that will be the quite good thing, because if someone plant has 5,000 years age, you will still see those atoms there. It takes in as much C14 as it excretes or exhales. So what is here we telling? As long as plant or animal is alive, it takes as much carbon as it excretes. So we're just talking about it takes as much carbon, it's taking as it is removing from the body. If we're talking about living organisms or exhale, if it's a human is going to exhale, if any plant is going to excrete. So when it dies, so that's what we're saying. When it dies, it no longer takes in C14. So the C14 in the organism slowly decreases. So this is what we're saying. So when something die, what happen is no longer takes the carbon 14. So carbon 14 is there in the nature, right? It's quite less, but when something die, it's not taking in, and so it's just decaying. So that's from where the life span of something, scientists discover. I mean, they're not taking the fresh, C14 isotope. They are just slowly decreasing. So that's why you will see scientists will tell you this plant is so many years old. This dinosaur, animal we found is so many years old. So that's no, you will know why they tell you, because those animals, they are not taking C14. When they were alive, they were the same, they were they were taking and excreting or exhaling, but what are they doing when they die? They are not taking, just decay. They're just decay. That's why, therefore, age of an organic substance can be determined by a C14 content. So you can do that. You can determine the age. We're going to just finish now after the atomic weight. I hope you were not tired right now. I gave you a little treat, right? By making a little bit more funny, right? The atomic weight, right? We're going to weigh. To whom we're going to weigh? Well, naturally occurring element. Wow, how are you going to put it, this one in a balance? The way you weigh yourself? Oh, can we do that? Well, we see what we do is the average weight of mass of its atoms. So we're talking about atomic weights. We did hear atomic, but what is the weight? Is the weight of a one atom? Is the weight of so many atoms? Is the weight of a guy? What is it? So it is a naturally occurring element. Weight of a naturally occurring element is the average. So the definition atomic weight we're going to talk about is an element, and naturally occurring element. And what is the atomic weight? You're going to say this is the weight of the naturally occurring element. Is the what is that? Is the average weight of average weight. What kind of weight is average weighted mass of its atoms? So we're going to weigh the atoms and average weighted mass of the atoms. So there will be the mass of the atoms, but we will take the average. And because an atomic mass unit is defined, now this is the definition of atomic mass unit. What is the definition? Atomic mass unit, you can abbreviate like that, AMU. So we define this word is defined as exactly. How do you define exact? So we're going to define exactly 1 over 12 of the mass of 12 carbon. So this is a carbon, right? And one atomic mass, we say, I'm going to make it a little bigger for you, right? So what is this we're going to talk about here, right? So AMU you did here is the defined exactly. What is exactly? 1 over 12 of the mass of carbon 12. So carbon 12, we said carbon 12 mean it has the mass number of 12. It has 6 proton, 6 electron, 6 neutron, right? And we weigh that one, and then we take 1 over 12. Like suppose carbon is 12 gram, right? And 1 over 12 will be 1 gram, right? And suppose carbon is like 12, I would say, pound, and how much the 1 AMU will be? 1 pound. So this is 1 over 12 mass of the carbon 12. This is called AMU. Now what is the atomic mass of 12 then going to be how much? Is 12 AMU. So it's just saying what is the atomic weight, right? The atomic weight of naturally occurring element is the average weight. Is average weight of mass of its atom. So whatever atoms it does have, we'll talk about how many atoms we consider here, but here it is saying this is average weight of its atoms, right? And atomic mass unit is just the mass 1 over 12 of the mass of C12. So we're going to say 1 over 12 mass, right? And atomic mass of 12 is of course, is going to be 12. So atomic mass of 12 is 12 AMU, and 1 AMU is 1 over 12, right? The atomic mass of carbon 13 is 13, right? 0.0034, right? This is 13 AMU approximately. Therefore, the atomic weight of the carbon is 12.1 AMU, because we were talking about the average weight, right? So they have taken the average, right? There are two kind of carbons, right? One is 12, which is 12 AMU. The other carbon, which is 13, and that's 13 point this one. So when they are going to take an average is going to be, more than 12. How do we take the average? This is the formula you must have to remember. The molecular weight is the sum of the atomic weight, right? The molecular weight is what? Is the sum of, what? Is the sum of, you're going to add atomic weight of all the atoms in the molecule, right? Now, this is 0.89. You're going to multiply this one. What is 0.89? And this is 0.00, 11. This is their natural abundance. Out of 100, they are present like that. We did talk about before, right? If I take you back, this was 98%, right? So, and other was, this one. So 1.1%. So that's why you see this decimal point just move here, right? And this decimal point moves here, this decimal point, all this decimal point, right? They are moving which direction? If we talk about the decimal point, it will move other direction towards left side, right? Two decimal points. So you will move this decimal point here, 0.98, and this decimal point will be 0.011. And then what are we going to do here, right? We're going to move, finish this one, atomic mass. This is atomic number. We finish. We're going to talk about atomic weight. And here we are. So this is just the decimal point we did move. You do see here two decimal point we move. And we're going to multiply with 12, because 12 is the mass of these guys. These are the guys, lighter guys. And the percentage is like that. They are 98%. So if you want to multiply them, we will multipy with them with 12. These guys, heavier guys, 13.034. Heavier guys, these are like that. And then you're going to add, this is going to be 12.011. So this is atomic weight. So this is the way we determine the atomic mass. Means whatever percentage was, we multiply with this all the weight, and then other percentage, these are the few guys in the nature. And carbon 13 one, they have more mass, but their percentage is less. So we are multiplying the percentage with the mass, right, of each guys, and then we are adding both the guys. Whatever is, this is 12 and this is molecular weight. The molecular weight is the sum. What we did here right now, we did something, we added something. So that's what you're going to write. It is sum. Sum of what? Sum of atomic weight. Atomic weight of whose guys? Of all the atoms. What kind of atoms carbon has? Two kinds. What are the two kinds? One is, these normal guys, right? 12 mass, and they are quite abundant. 12 atomic mass, 98.89%. So we just moved decimal point 2 point here, because we are talking about to have the value of 12. We're just multiplying them with their percentage. You can say we have divided this one with 100, but before 98, and we had divided this one 100 as well. This one was 1.11, so we have divided this one 100. What our answer is, we have written here, and we are multiplying them with their atomic mass, whatever was. They have 30 atomic mass, is well done, is okay for us. We're going to multiply these heavy guys with whatever their percentage is. This was a percentage, so this number is here. We have percentage, we have divided this 100, the percentage was 1.11. We have divided this one 100, the answer is this one. The decimal point, we move to the left side, this is 0.01111, and now this is a 12. and this was a 12 guys, lighter guys, right? And their percentage was 98.89, so it was just 11%. Here was just 11 less than 99%. So what we did, we divided this one with 100. We have this figure, we multiplied both these, we added all the answers of this one and this one. So what is this atomic weight, molecular weight? This is a